Continue. Beautiful. Thank you for reminding me. All right, we good? Ready to do question number 4? All right, question number 4. An electron is accelerated by a potential difference of 0.1 volts. How much greater would its final speed be if it were accelerated with 4 times as much voltage? Right? So this is essentially an energy conversion problem. Anyone have a suggestion for the answer? If the change in energy is 0.1 volts and the changes to kinetic, what happens to the velocity if it's 0.4 volts? When it changes to kinetic, what happens to the velocity? Any thoughts? Anyone?
The velocity doubles.
The velocity doubles. Excellent, right? The velocity doubles because its kinetic energy is v squared. So a 4-time increase in change in energy is 1/2 mv squared. 2v squared, right? So we'd have to double the velocity. So 2 squared gives you 4 times as much energy. Beautiful. Excellent answer. Number 6, can a particle ever move from a region of low electric potential to one of high potential and yet have its electric potential energy decrease? So can something move from low potential to high potential and have its energy decrease? So here we go again, right? High potential, low potential, and we're going to move our charge from here to there. In that process, can it have, even though we're moving it to an area of high potential, is it possible to decrease the potential energy?
Yes.
Yes. How would that happen? What would have to happen?
It said it was like an electron, right?
What's that again?
Oh yeah, the particle would have to be a negative.
Excellent.
To be able to move from low to high, and then the potential energy decreases because the distance between like the original, I guess, the same increases, right?
Yes. So if this is a negative, right, if this is a negative charge, if our test charge was negative, then as it moves, even though it's in an area of low potential, it has a high potential energy, right? Because potential, the voltage is KQ over R, but the potential energy is KQQ over R. So the two negatives are going to mathematically become a positive. So this has a high positive amount of energy, whereas we get close to here, we get a negative amount of potential energy, even though the electric potential is an area of high potential. So excellent. That's an excellent answer, right? So we're moving from low potential to high potential, but we're moving from high potential energy to low potential energy. All right. Again, the difference is.
Sorry, one question is like, what is like the so what is the difference between potential and potential energy?
Okay, so I had this discussion with Sammy yesterday after everyone left, so he's going to hear it again. The difference is essentially the potential is what is produced by the source charge that's producing the electric field. The potential energy is how much energy that thing in the electric field, that test charge in the electric field has. So I made the analogy to gravity, right? So gravitational potential energy is mgh, right? So here's Earth, and it's some height above the Earth. I can place two different objects, right? I can place a really big object, a large mass, or a small object, a small mass. They both have the same potential to fall. The potential is the electric or the gravitational field at some height. That's the potential, right? It's going to accelerate down from some height. And we know everything falls, assuming no air resistance, everything falls at the same rate, right? So no matter whether it's large or small, it's going to be going the same velocity at the end. So this is the potential for the gravitational field. The energy depends on how big the mass is. So the large mass has more energy, even though it has the same potential.
Okay, gotcha.
Right, and the same thing happens for our charges, right? Our potential is defined as a high potential here because V is KQ over R. So when I place the energy is then, this is the potential due to the charge. The energy is then this charge within that field. Right, so our energy is Q, KQ over R. Right, does that make sense?
Yep, gotcha.
Okay, good. All right, let's move on to our last question, number 8. If V equals 0 at some point in space, must the electric field equal 0? And if E equals 0, must V equal 0 at that point? Explain. Again, this is what we did yesterday, right? And I actually already talked about, right? This case. Is there a place where the electric field is not 0, but the electric potential is 0? Right, again, this was that situation yesterday, right? That somewhere in the middle between the two, depending on their values, if they're the same value, it's exactly in the middle. At that point, V equals 0, but E is that way, right? The potential is 0 because this is low, this is high, so somewhere in the middle is 0, but the electric field is not. Good. And then is there some place, is it possible to have the opposite happen, where the electric field would be 0, but the electric potential to not be 0? And I would say that that's yes also. If I make both of them positive, then right in the middle, the electric field is going to be 0, right? Because they're going to cancel each other out. But the electric potential is going to be something greater than 0. Right, because the KQ over R plus KQ over R is going to give us something greater than 0. Good? Okay. Okay, I'm going to take your silences. You got it. So those were the 4 questions that I wanted to deal with. And then there are 1, 2, 3, 4, 5, 6 problems I wanted you guys to work on. What time is it? So we have plenty of time here. So why don't we do this over the next couple of days here? Take a few minutes, all right? We're now on page, I'm looking on page 489. Let's take a few minutes and do number 16. You guys can work on it together, work with each other, or work on it individually. Do number 16, and then in a couple of minutes, we'll go over it, make sure that we're good. All right? How's that sound? I don't even know if you guys are still with me.
Sounds
Turn
good.
off your cameras.
Yep.
All right. So work on number 16, and then in a couple minutes, when we feel like we're ready, we'll go over it together. I'm here to answer any questions as you're working, if you have any, or you can help each other, which would even be better. Lost my rag, there it is. How we doing out there? Awful quiet out there. Anyone need any help? Have any questions? Let me do this here. All right. Can you see the whiteboard here? I moved the camera, so,
Yeah, we can see it.
okay. In number 16, we're asked how much work does it take to move a 0.5 microcoulomb charge from halfway between two other charges to a place that's in between. So let's say we have this is positive 35 microcoulombs. And we have our other one that's positive 35 microcoulombs. And we're going to move our test charge, which is positive 0.5 microcoulombs, from right here in the middle to somewhere over here. Right, microcoulombs. We're going to move that there. Right, that's the idea. And how much work does that take? Work is change in energy. right? And energy is, or the change in energy is final minus initial. Good? Does that make sense? So this has to be U final minus U initial. All right. So electric potential energy, all right, electric potential energy is Q times V, which is Q times K capital Q over R. We good there? So our final energy would be Q times the KQ over R from one of the points plus the KQ over R from the other point. Right? So this is, if the whole thing was 32 centimeters apart, and we've moved them from a point that is right in the middle is a distance of 16 centimeters each to a point that's 12 centimeters from this one, which means it's 20 centimeters from that one. So this is 0.12 meters, and this is 0.20 meters. Okay, that's my final, that's our energy final. Our energy initial would be Q KQ over R, where the R's are the same. So 2 KQ over R. We okay here so far? Anyone need, please speak up if I'm not making myself clear, or if you're not sure what I did. Now I'm just gonna do a little, make my life easier. gonna-
Mr. Shukit,
Yes,
wouldn't the KQ over 0.12, wouldn't that be 0.04 because you're 12 centimeters closer to one of them?
doesn't it say,
12 meters closer.
did I misinterpret it?
Closer.
You're moving it to a point 12 centimeters closer to either, oh yeah, so you're right. So it should be, I misinterpreted it.
That's all
So
good.
this should be
0.04.
0.04 and 0.28
Yep.
and 0.28. Yes, I agree. You're right, I did misinterpret that. Because we moved it from here to 12 centimeters closer. It was at 16. So now I'm gonna move it 12 closer to 4 centimeters. That's good. This R is 16, right? 16 centimeters or 0.16.
Yep, correct.
Good. So now I'm gonna, here, right? I'm gonna pull this stuff out. Q, KQ 1 over 0.04 plus 1 over 0.28 minus that whole thing. That we should be able to do, right? 2 over 0.16 Q KQ. Right, so my numbers are wrong then because I did it the way I originally did it, but the idea was right. So I have to redo my numbers on my, when I worked it out. But now it just becomes a matter of pushing buttons, right? The small q is the 0.5 microcoulombs, K is our constant, 9 times 10 to the 9th. The large Q is 35 microcoulombs. So what is this? 1 divided by 0.04. Is that it? We're done? Right? Are we okay with that? You can finish putting in the numbers if you need to. So do me a favor. let's try and do the next two. Try and do 19 and 21 tonight, and we'll look at them tomorrow together, okay? Let's try and do numbers 19 and 21 and have them ready for tomorrow.
All right.
All right?
I see.
Yep.
Good.
We'll see you. So long, guys.